Adventures in Mass Spectrometry, rather general title. I'm going to introduce these people, Gary, because you always have a way of bringing hundreds of people to Pittcon in your lifetime, and I'm sure some of these are going to be outstanding presenters in the future. His co-authors from IU Bloomington are Stephen Ray, Jake Shelley, Christy Yankee, Alexander Graham, Elise A. Dennis, David Coppenall, Charles Barnaga, and Justin Wiseman.
It's always a tough business to try to follow Alan Marshall.
Yes, it is.
Great. Thank you, Jack, for the kind introduction. But as I said, it's really a delight to be able to be in Alan's symposium. I have to get my computer started again. It says I have to give a talk. Great. Well, I'd like to, first of all, apologize for the rather general title that I've used here, Adventures in Mass Spectrometry. That is, of course, a very general title, and I hope to become a little bit more specific in a few minutes. But as I started out by saying, it's very difficult to follow a guy like Alan Marshall. He presents such a wonderful talk, and the science is, of course, just excellent. But let me tell you a few other things that might add to your perspective on Alan. As Jack said earlier, Alan's only the fourth person to have won all three major awards from the Pittcon. But one thing that Jack didn't say is that there won't be any other people who win all three of these awards because the Hasler Award is no longer being sponsored, so you won't see that again at the Pittsburgh conference. I hope that that changes, but so far that's the case. Something else that you might not be aware of is the fact that he's going to be the recipient later this year of the William H. Nichols Medal, which is, I think, the oldest ACS award. Not only that, but some 16 Nobel Prize winners have in the past won this Nichols Medal. So it's a very, very high level of distinction. I want to start my talk, before I really give you the true title, by highlighting some milestones, at least my milestones in mass spectrometry. Some of them might be different from what you'd pick, but I think they're still pretty darn important. For example, the first discovery of stable isotopes was by mass spectrometry in 1919, and Aston won a Nobel Prize for that in 1922. These are all chronological, by the way. In 1953, the ion trap was developed. It wasn't published at that time. This is the Paul ion trap. And, of course, Wolfgang Paul won the Nobel Prize for that in 1989. Next in sequence is what Alan Marshall did. He and Mel Commissaro in 1974 discussed Fourier-Transform mass spectrometry, first described it, and, of course, developed it since then. ESI came on the scene a bit later in 1984, and John Fenn was a co-recipient of the Nobel Prize in 2002. And lastly in my list is MALDI, and in 1985 that was developed, and Tanaka shared a Nobel Prize in 2002. And if you look at this list, there seems to be something missing. There's one subtext. If you look at the yellow ones in particular, it seems like there should be a subtext right here. We'll see if that comes about. I think that, of course, Jack is exactly right about the National Academy, but I think that this work really deserves a Nobel Prize, not just the National Academy. And I'm calling on Alan so that if he should win the Nobel Prize before he's elected to the National Academy, he will decline the National Academy. See if that happens. Okay, here's the real title of my presentation. Distance of flight mass spectrometry, and I put this little etc. after it because I'll be talking about a couple of other things that derive from distance of flight mass spectrometry. The people who did all this work are shown here. Chris Enke is the idea man. He really came up with the idea of distance of flight mass spectrometry. In a 2007 paper, he and one of his postdocs described it. The guy at Indiana who really implemented this, who reduced it to practice, is Steve Ray. Steve Ray is the guy who actually built a distance of flight mass spectrometer. In fact, he built two of them, and he built them both for the princely sum of $30,000, not an exaggeration. Alex Graham is the grad student who's been working on this, and just yesterday we found out that Alex will be the recipient of a Division of Analytical Chemistry full-year fellowship. Great guy. Elise Dennis is the newest person on the team, and she will be giving some material later on in the year. But she's the innovator in one other area that I'll talk about later in the presentation. We have then our co-conspirators from Pacific Northwest National Laboratory, Dave Coffenall, Charles Baranaga, and their postdoc, Tony Corrado. But first I better tell you what distance of flight mass spectrometry really is, and I think that can be done most easily by comparing it to a much more familiar method, and that's time of flight mass spectrometry. So here's time of flight mass spectrometry. This is distance of flight mass spectrometry. Now I think you're all aware that in time of flight mass spectrometry, what we do is to accelerate all ions to the same kinetic energy. They fall through a given voltage drop between these two electrodes, and that gives them all the same kinetic energy, nominally anyway. And that kinetic energy, of course, is equal to 1/2 mv squared, where m is mass, v is velocity. So the lighter ions fly faster, they go through an ion mirror, and the lighter ions arrive at a detector sooner than the heavier ions. So the time-dependent output of the detector is, in fact, our mass spectrum. Distance of flight mass spectrometry is very, very much the same, except people who use it aren't quite so patient. We don't wait for the ions to emerge from that flight tube. Instead, what happens is we give all the ions a mass-dependent velocity, really a constant momentum. I'll talk about that a bit more in a few minutes. They go through an ion mirror, they fly down the flight tube, again a field-free region, and before the lightest ion of interest emerges from the flight tube, what happens is all the ions are pushed sideways onto a spatially selective detector. So the lighter ions will wind up down here, the heavier ions, which were going more slowly, wind up over here. So of course there are a lot of similarities between the two, but there are also some important distinctions. First, in terms of similarities, they're both velocity-based separations, one kinetic energy, one constant momentum, but still they're velocity-based. Both provide full spectra for each ion badge, so we get all the ions at the same time in both of these that are captured in the snapshot from this thing that we might call an extraction zone, the region where the ions are extracted. They both have very high spectral generation rates, depending on the mass range, of course. Typically, we get about 20,000 or so mass spectra per second, so very, very fast. And both have no upper mass limit. As you heard from Alan Marshall's lecture, what happens is, of course, in most of the other methods of mass spectrometry, it's impossible to look at really, really heavy things if they're singly charged. So here we don't have that problem. There is no upper mass limit. Theoretically, if we had nothing such as gravity to worry about, we could throw a bowling ball down here. And in fact, people have looked at intact viruses with these devices. There's a bunch of distinctions, though. The two main ones are really the result of the detector. In time of flight mass spectrometry, we expect one detector to do all the work. And it has to be a very high-speed detector with very fast electronics. If we have the very fast electronics, then everything works fairly well. In contrast, here we have a whole bunch of detectors, one nominally for each mass-to-charge ratio. So as a result, each detector can have a gain, for example, that's tailored to that particular ion flux. That makes it much more flexible, gives us a broader dynamic range. So we don't have to worry about pulse pileup, for example, in distance of flight mass spectrometry as we do in time of flight mass spectrometry. So again, the big difference lies in the fact that we have an array of detectors, nominally one for each mass-to-charge ratio, rather than only a single detector. Another thing that's important is that this is really a spatially selective device. It's possible, for example, to collect the ions that are then mass separated, because now they're all falling in different spatial zones. We could collect those ions and do different things with them. There's a device called an ion separator, a mass separator, that was used way back in World War II, in which they separated the isotopes physically onto different collectors. And of course, those were based on typically the segment system, sector systems, because they needed to look at the different locations. In that case, we had to have a magnet. We couldn't look at very high masses. In this case, we don't have that problem. One of the problems here, though, is that the methods that are ordinarily used in time-of-flight mass spectrometry for energy and space focusing don't work in distance-of-flight mass spectrometry. And that's the next thing I'd like to talk about, these different focusing methods, which really rely on this constant momentum acceleration rather than constant energy acceleration. And a lot of this was described by Chris Enke and Gareth Dobson in their pioneering paper in 2007. So here's the idea of constant. What in the world is this? Are we going to be kicked out of here? I think this is actually an alarm. Wow. Who cares? Let's just go. Let's have a good time. Here's the difference again between time-of-flight mass spectrometry in the top and what we'd have to do in distance of flight mass spectrometry in the bottom. In conventional time of flight work, remember, we use constant energy acceleration. In distance of flight mass spectrometry, we use constant momentum acceleration. Here's what happens. As I indicated before, in constant energy acceleration, conventional time of flight mass spectrometry, we have our ions between two plates. We then apply a voltage to the plate that shoots the ions out of that region so that both, or all of the ions rather, fall for the same voltage drop. They all get the same kinetic energy, and the energy, of course, as I said, is equal to 1/2 mv squared. In the case of constant momentum acceleration, what we want to do is give all the ions a given kick. And we do that by, first of all, applying that voltage that gives these ions a kick that makes them move a little distance, but before they leave that extraction zone, we turn off that voltage pulse. So all the ions get the same impulse, therefore the same momentum, and because they get the same momentum, and momentum is equal to the mass times the velocity, again, the lighter ions, the ones with lower mass, have higher velocity, but kinetic energy is equal to 1/2 mv squared, just as we have up here. So if the lighter ions have a higher velocity, of course, if we square the velocity, that means that the lighter ions have the higher kinetic energy, larger ions have lower kinetic energy, and the energy then drops off as the square root of the, quadratic relationship here exists. Here's how the system works. We start out with a bunch of ions here in our so-called extraction zone. We'll give them all a given kick. Here's our constant momentum acceleration pulse. And some of the ions might be moving in the direction of the flight tube. My pointer didn't work. There we go. Some of the ions might be moving in the direction of the flight tube. Some might be going in the opposite direction. And they'll have to turn around. Now, that turnaround time can cause serious errors in time of flight mass spectrometry, but it turns out they don't in distance of flight mass spectrometry. What happens is when the ions go through an ion mirror, the higher energy ions go farther into the mirror, but they all arrive back at this location down here at exactly the same moment in time. So at this particular time that we call the energy focus time, I'll abbreviate it sometimes EFT, that energy focus time is the place, or the time rather, when all the ions will be in focus. But lighter ions will have traveled farther, and heavier ions will not have traveled quite as far. So at that given time, they'll all be in focus, all be in energy focus, but at different locations. And that's what constant momentum acceleration is used. We can perhaps understand this better by looking at the Simeon simulation. In this case, what we have is the location in the flight tube where the ions are. It's a function of flight time. And what we have are 3 mass-to-charge ratios, 60, 80, and 100. And all of these have been given a range of kinetic energies, actually a total range of 2 electron volts. Plus 1 electron volt means in the direction of the flight tube, minus 1 electron volt means that the ions are going in the wrong direction. And you can see for each one of the mass-to-charge ratios that the higher kinetic energy ions penetrate farther into the reflectron, but they all come into focus then at this so-called energy focus time. That's the flight time where all of these ions are in the best energy focus. That's, of course, where we place our detector. We place our detector, whatever it might happen to be, at that location, and we'll see mass 60, 80, and 100 in focus at different locations along that detector. Notice also that the ions get a little bit crowded up at the top. The distance between 60 and 80 is considerably larger than the distance between 80 and 100. In fact, the distance of flight is proportional to the inverse of the mass-to-charge ratio. So the ions do get a bit closer together as we go to higher masses. Well, with all that as background, in fact, background that Chris Anke and Gareth Dobson produced, we decided that we would build a couple of these instruments, one of which is at Pacific Northwest National Labs. And this is the way the system started out looking. This is the idea behind it. We started out with a glow discharge source that's really been our source that we've used most of the time. It has a broad energy spread, so it kind of stresses the system. It also produces a diffuse beam of ions, so unlike MALDI, it's a little bit harder to focus, but it also is very easy to set up. So we use this glow discharge source, focus the ions a bit with a quadrupole doublet, so they have the right shape coming into this extraction zone. They're then shot at a right angle, go through a linear reflectron, come back up, and then they're shot upward out of the plane of the screen towards you onto a spatially selective detector. Notice that all the data I'll be talking about at first here is with a very short flight length. It's only a 35 centimeter flight tube, so it's a very, very short time of flight mass spectrometer. This is the way the thing looked. The machining diagram, I'll stop it right there and show you here's that quadrupole doublet right here. Here's our extraction zone. The ions are shot into the reflectron, come back out here, and there's a little hole you can barely see here through which the ions are shot upward. I think that this is really the best perspective to show the ion optics. Here again is our quadrupole doublet, our extraction zone. The ions are moved off into the reflectron. They come back here, and then they're shot upward onto a spatially selective detector, as I said. Well, we started out with a very simple spatially selective detector called an electro-optic ion detector. We had one available. They're actually very versatile, very convenient to use. Very simple device, a couple of microchannel plates and a phosphor or scintillator plate. The way it works is that if there's an ion that strikes one of these little holes in the microchannel plate, it produces a shower of electrons. Each one of those electrons is accelerated to another one of these microchannel plates. So each one of the electrons from the first plate produces a shower from the second plate. So a whole cascade of electrons then hits this phosphor or scintillator, produces a bright spot that we can see with a conventional CCD camera. Very, very easy device, nice for testing a system such as this. This is the way it looks from the side. Here's that microchannel plate. It's really a pair of microchannel plates and the phosphor sitting up here with a high voltage across them. And the ions would then come right in this region. In fact, let's see if we can see the ions. Here are the ions in that region. The ions will go into the plane of the screen and then be moved upward onto that microchannel plate to produce a bright spot on the phosphor. So all those ions which had the same mass to charge ratio would be located or produce a little strip or stripe on that phosphor up at the top. Here's the way the system looks installed in our distance of flight mass spectrometer. And this is the way the spectra look. What we have here is in room light, we can kind of see some stripes, turn the room lights off, and we can see that in fact these are isotopes of tin. So this is just a phosphor that we're taking with a conventional camera. Well, how well does it work? You can see some of the data here in this 2011 last year publication from a research group. But if we look at it a little bit more carefully, we find that it's not as good as we'd really like. For example, here are some zinc and copper isotopes. And if you see the size of the stripes from this line scan across that phosphor image, they're really pretty broad, 1.5 or so millimeters. That's really a broad stripe. It should be much better focused than that. And we wanted to find out what the problem was. Of course, what that results in is really moderate resolution. We need better resolving power than that. So we tried tracking down what the problems were. And of course, our first suspected culprit, at least, was the microchannel plate. That wouldn't be so bad if we were stuck with copper or chromium or something like that, or even in copper and zinc. But when we get up to the higher mass region, where we start getting the crowding of the peaks that I talked about before, here in the tin region, here in lead, we no longer even have baseline resolution. So that resolution really isn't adequate, even for atomic spectrometry, never mind petroleomics or even proteomics. Well, as I said, I think the culprit was, we figured the culprit was probably this electro-optic ion detector. Literature shows that, in fact, our experience shows also that the spot's broader than the incoming ion beam would be. And of course, that's not too surprising because we have a shower of electrons produced by this first microchannel plate, even more electrons produced by the second one, and the electrons don't like each other. They'll repel each other just by Coulombic repulsion. And the space charge is going to broaden that beam, so the beam is really going to be pretty diffuse out here when we finally look at it with the CCD camera. That meant we had to have a different kind of detector, one that didn't involve so many electrons. The electrons we figured were the culprit here. So this is the device we turn to next. It's a solid-state array detector. We've been working on it with Bonnardette and Dave Coffenall for a long time now. We've used it with a Mattock-Herzog geometry mass spectrograph. Now we're applying it to this distance-of-flight mass spectrometer. We call this device the focal plane camera. It really consists of a whole bunch of Faraday strips, little strips that simply collect the charge. We have two different cameras that we've been using. The one that I'll talk about today has 512 of these channels. Another one has 1696. And there are other devices that have many, many more strips than that. The nice thing is, as I said, it's a charge detector, and it directly integrates. So it also gives us a broader dynamic range. This is the way it works. It's a very convenient device to use because basically it's simple electronics. In his lecture yesterday, Sandy Dasgupta talked about electronics. Well, this is a really simple electronic circuit. It's an operational amplifier with a capacitor, in fact, two capacitors in the feedback loop. That's just an integrator. So when a charge comes down and hits that Faraday strip, the charge is collected on these little capacitors, and the charge then produces a voltage output at the output of that operational amplifier. In fact, because The capacitors here are so small, we actually get a pretty substantial voltage step. The magnitude of that step is inversely proportional to the capacitance here, and of course it's a direct charge integrator, as I indicated before. It integrates the current over time. Notice also that we have two capacitors in that feedback loop. 8 femtofarads, that's a tiny capacitor, and 8,000 femtofarads. This one on the top can be switched in whenever we need it. It doesn't have to be there. What that means is that we can have one tiny capacitor, or we can have a large capacitor with another one in parallel with it. So what that means is that we'll have two different switchable levels of gain depending on whether we have the top capacitor switched in or not. And what that produces in turn is two levels of gain, as I said, that differ by a factor of 1,000 in their gain. Well, each one of the Faraday strips has its own circuit like this, and each one of the Faraday strips then can be addressed independently and in any order that we wish by this multiplexer. If one happens to be collecting a very high flux, we can reset it, read the output here, reset it, and start integrating over again. So that's one of the reasons that we can get this very broad dynamic range, because we can set the gain on a channel-by-channel basis and integrate for different periods of time for the different channels. Very convenient device, as I said. Most of the work that I'm going to talk about today used a 512-channel device. It also reads out fairly rapidly. It takes about a millisecond for each one of the spectra. So it's quite a fast device. One other attribute is something I mentioned before, but I think I should justify it. In a conventional kinetic energy detector, such as a microchannel plate or the other types of detectors that are commonly used, a biomolecule often doesn't produce a signal because its translational energy, its kinetic energy, is converted to internal energy when it hits the detector. As a result, it doesn't kick loose an electron from the detector. In contrast, if we have a charge detection device and have a charged biomolecule, that charged biomolecule hits the detector, deposits a charge on the detector, and that little operational amplifier will collect that charge. In other words, we'll get the same signal from a biomolecule that's singly charged or from something like an atomic ion, a cesium ion, or something like that. This is the way the device looks that we had to put into the distance of flight mass spectrometer. Distance of flight increases in this direction, so the lighter masses would be over here, the heavier masses over here. The plumbing was a little bit complicated because this thing has to be cooled down to at least dry ice temperatures, so we have cooling lines going in and out, but it wasn't too hard to install into our distance of flight mass spectrometer. And as we expected, the resolving power, in fact, increased quite substantially. In this case, again, we're looking at the lead isotope, 3 of the lead isotopes, and the resolving power is considerably higher than it was before, over twice as high. So now we have baseline resolution even in the higher mass range. So that looks quite satisfactory. It's not quite as good a resolution as we think we can achieve, but it's pretty decent. There is, however, a problem that you might have detected. The region in the mass range that we can detect, the range of the masses, is really limited by the size of this detector array. So we need a really big detector array if we want to look at a very broad mass range. Now, these detector arrays can be put next to each other, and larger arrays are being built all the time. But still, that's a limitation. And we wanted to explore alternatives to looking at a really broad mass range with a really large and really expensive detector. But there are other things that we can do. For example, one of the things we can do is just to push the ions up onto the array detector at different times. So here we have a difference in delay time, and if we delay a little longer, another mass range will be launched up onto that detector surface. So we can look at a small mass range and the adjacent mass range and so on. In fact, that's what we see here. There are really 3 different scans of a tin sample, and you can see that the tin 120 isotope comes at different locations on the detector at different times. Well, that's okay, but there's something I mentioned before that was really critical, and that's that there's a particular time called the energy focus time where all the mass discharges are in energy focus at different locations. So if we change the time of detection, what that means is we either have to change the ion optics or we'll have some defocusing going on. And in fact, if we align those peaks from this particular spectrum, just align those peaks, look at all the different tin isotopes, what we find is that the best focus is for the tin 120 isotope. That's the one that we really set things up for. And if all we do is delay that extraction, that movement of the ions upward onto the detector surface, we get a little bit poorer resolving power. And if we go farther and farther away, the resolving power gets poorer and poorer because we're looking at different times. And remember, the ion optics have to be set up for a particular energy focus time, a particular time when we launch the ions onto the surface of that detector. So what else can we do? If we don't want to try that, what we can do instead is to use the same instrument. It's the same instrument I've been talking about here, a distance of flight instrument. Here's our detector. We can also use it as a time of flight instrument. That is, what we could do is to collect a time of flight mass spectrum in the conventional way using a time of flight detector, and when we want, we can capture a distance of flight mass spectrum for a particular mass range, even if we have a detector of limited size. What is that going to do for us? Well, this is the same instrument in a time of flight mode. So here we have a conventional time of flight mass spectrum. That time of flight mass spectrum will capture as broad a mass range as we need just by looking at later and later times. But now what we'll do is look, for example, at this copper region, but we'll do that in both the time of flight spectrum. We'll expand the spectrum, and we'll compare that then to a distance of flight mass spectrum for the same mass range. Here's the time of flight spectrum of that region. We can see that there are copper and zinc isotopes in that region. We couldn't see it in the poor resolution scan in the last slide. But if we compare that now to what we get for a distance of flight mass spectrum, the difference is pretty doggone obvious. We have a higher signal to noise here, have a lower baseline. We don't have the electronic noise that you get in a time of flight system because we don't need such high speed electronics. And then that makes the spectrum much cleaner. So there's a reason then to do a full time of flight spectrum, but then to look at a narrower mass range with a distance of flight system, even if it's a limited mass range. Another thing we can do kind of stems from some of the other things that I've talked about in the earlier part of the lecture. We can do something we're calling zoom TOF. Forget now for just a moment about distance of flight mass spectrometry. Now what we're going to do is to use two different modes of operation in time of flight mass spectrometry. First of all, we'll have conventional time of flight mass spectrometry, constant energy acceleration, maybe a two-stage reflectron. We'll get a time of flight mass spectrum. What we can then do is to select different conditions, in particular constant momentum acceleration, that'll help us zoom in on a particular region of that spectrum. Let's say, for example, we want to look at this region, but in higher resolution. We can use constant momentum acceleration in a way that I'll describe in a few moments. And what that will do is to spread these peaks out, give us much higher resolution for that narrow range. So that's why we call this zoom TOF. It's very analogous to what we have, for example, if we have a zoom lens. That's really a big zoom lens, but if we have a zoom lens on a camera. If we have a broad field, we'll have a broad mass range. But if we want to have high resolution, we have to narrow the mass range in order to see it better. The nice thing about this is we can get high resolution without sacrificing sensitivity. What I mean by that is that ordinarily in time of flight mass spectrometry, the only way to get better resolving power is to have a longer flight tube. Just take longer. In fact, flight tubes are now available going back and forth or in figure-8 motions of 20 meters or even more. The problem there is that if you have a 20-meter flight tube, you have to wait a long time before the next ion pulse is put in. That lowers duty factor, and as a result, sensitivity is lost. Signal-to-noise ratio is lost, just because the duty factor is lower. In addition to that, with this constant momentum acceleration time of flight mass spectrometry, we can get an even higher duty cycle because what we can do, since we're looking at only a narrow mass range, we could use a pre-filter or some other approach to restrict the mass range that we observe to that very narrow one. Because it's a narrower mass range, we can actually increase the repetition rate of the ion injection and therefore improve duty factor even more. So the duty factor should be considerably higher in the zoom mode of operation. We retain a lot of the other advantages of time of flight mass spectrometry, an infinite mass range, simultaneous ion extraction. With a higher resolution, we can overcome a lot of spectral overlaps. And something that you should keep in mind now for the next few minutes is that you could incorporate this into your existing time of flight system. Manufacturers could build new instruments with it, or if you wish, you could retrofit your existing time of flight system for this higher resolution mode that has these advantages. Well, how really does it work? Remember what I said about distance of flight mass spectrometry. We're using constant momentum acceleration, and as a result, there's a particular moment in time, the energy focus time, when all of the ions are in energy focus but at different locations. So if we had three different masses, one that is less than the target mass, one that's greater than the target mass, and the target mass itself, what will happen is, of course, the lighter mass will have flown farther. It'll be over here. At the same time, the target mass will be right here, and then the heavier mass will be down here. So at that energy focus time, under constant momentum acceleration conditions, all those ions will be in energy focus. And that's, of course, the basis for our distance of flight measurement. We just have a spatially selective detector to look at the ions all in focus at that particular time. Now, if we choose, we can put a detector then right at one location, any one of the locations here. But if it happens to be right here, this ion will be in energy focus, and the other two ions will not be. This one will have already passed that point, and when it went through that point, it'll have a broader peak. This ion has not yet reached this point, so it will be out of focus as well. And that's, of course, what we'd have in a time-of-flight system under constant momentum acceleration conditions. The one ion and the peaks around it, of course, will be in good focus. The other peaks will be out of focus. But this focus will be far better than we can achieve in conventional constant energy acceleration time-of-flight mass spectrometry. Well, we built a different system for this because we wanted to run both operations at the same time. So again, an orthogonal acceleration instrument, again, only 35 centimeters in flight length. Fairly simple geometry, as you can see. Here's our region, our extraction region. We can steer the ions into the reflectron. It's a single-stage linear field reflectron. The ions go in here, come back, and they then hit this detector, a conventional time-of-flight detector. If we compare the two modes of operation, here's the conventional mode. Again, we have a full spectrum. This full spectrum then is achieved under constant energy acceleration conditions. Again, we have a glow discharge ion source, only 35 centimeter flight length, and the resolving power we get here is not quite 600. Not too bad, but not great enough for a lot of the things we'd like to do. However, what we'll do then is to zoom in on, in this case, this lead region. If we zoom in on the lead region, under constant momentum acceleration conditions, here's what we get. Much, much narrower peaks. This is constant momentum acceleration, and the resolution, the resolving power, jumps to over 4,000. So we get much, much better energy focusing than we do under constant energy acceleration conditions. Look at another spectral region. Here's a group of 10 isotopes, and they illustrate, I think, one of the things that I mentioned before. In this case, what we're doing is we're focusing in on the 116 isotope of tin. That's this one right here. And we get the best resolving power there, about 4,500. If we go farther away, 117, 18, 19, and 20, you see the resolving power degrades just a little bit because those ions aren't really at the proper energy focus time. These ions, because they're heavier, hit the detector later. The ions over here hit the detector earlier than the energy focus time. So they're a little bit out of focus, but you see they're still getting pretty doggone good resolution around that area. If we go to a larger flight tube, which we've recently done, about twice the flight length, we had 0.35 meters before, here at 0.68 meters, you can see that the resolving power scales directly. Now we have a resolving power of about 8,000, about twice as much. And again, this is for less than a meter, 0.68 meter flight length. So it's pretty decent resolving power, especially for a glow discharge source, which, as I said, has a broad energy range and a fairly broad ion beam coming out of it. Some of this work is going to be discussed in much greater detail tomorrow by Steve Ray, lecture 1900-5. That'll be 4:25 in the afternoon tomorrow. So Steve will talk a lot more about the zoom TOF in particular and how it can be used for higher resolution. One last thing I wanted to mention is that we have another mode of operation here that's kind of interesting. We can, I mentioned it before, but the idea here might be, for example, to use MALDI. It wouldn't have to be, but we could use MALDI. So we shoot down here, we generate our ions, we'll shoot those ions out under constant momentum acceleration conditions, and they'll fly down then to the detector region. Once they reach this detector region at the energy focus time, they'll be pushed upward onto this array detector. And of course, each one of the arrays, the points in the array is going to have its own integrating system, so we get a peak from that. That's what I've told you about before, but one thing we could also do is to then remove this system from vacuum or have a different location or a different surface rather, and once we have that, we could do different things with it. We could, for example, have preparative scale collection. We could treat the species on here biochemically. We could do activity assays for either biomolecules or do nuclear analysis as well. So this collection device is something we're now building, and we hope to be able to exploit them in the future. So what I've talked about here today are really 4 different approaches to mass spectrometry. Distance of flight mass spectrometry, the combination of distance of flight and time of flight mass spectrometry, zoom TOF, that way of using time of flight mass spectrometry with constant momentum acceleration, and preparative or soft landing distance of flight mass spectrometry. So there are a whole lot of new things for us to play with and to think about. I'd like to end the talk by thanking all the institutions and agencies that have sponsored this research. Pacific Northwest gave us some early seed money. The DOE Office of Science has helped us a lot. We've gotten a lot of components from LECO. NSF now supports its soft landing work in the Indiana 21st Century Fund. And with that, I'd like to thank all of you for attending and also congratulate Alan once more for an outstanding career and an outstanding presentation. Thank you very much. Are there questions? I can't see you very well, so you'll have to speak up.
So, Gary, on the very last slide that you showed,
Yeah.
the first isotope on ringing after it, or the second isotope, the baseline just went down to the distortion factor. Is that a resonance effect, or is that just proportional to the signal?
That's just shitty impedance matching.
Okay.
We have an amplifier that rings. We have to get a better amplifier. Has nothing to do with the mass spectrometer. Alan, yeah. The question, in case you couldn't hear it, was from Alan Marshall. He asked what limits the number of channels we have in the detector. Basically, it's the size of the silicon piece. It's an integrated system with the little charge collecting strips, the Faraday strips, right on the top of the integrated circuit. So it requires having a much bigger piece of silicon. We're also developing something that will enable us to end-butt these, so we can have one of the chips next to another chip. Right now, Spectro has a mass spectrometer based on the Mattock-Herzog geometry that has a chip that's over 4 times as large as ours. And there's no limit to how large this thing could really be made if we simply put them next to each other. But it's just the size of the silicon chip. We could make the strips narrower, but there's no real gain there because we already have narrower strips and we have a focal point. Any other questions?
Thank you very much.
My pleasure. Thank you.